Okay, let's begin. Questions on the homework. 11 points. What's the first one? That's the implicit differentiation one. Chain rule and implicit differentiation section. Okay. Number 7, you said? 37. What does that say?
Let me get my homework.
It says x equals r cosine theta, y equals.
Wait, what did it say about this?
Yeah, it did give you a function for that.
Okay, so x equals.
R cosine, this equal importance. X equals r sine theta. And then it asks you to find dz dr. But it doesn't give you like a function. I'm sorry, it says that is on but that's all it says.
Partial z with respect to r.
Yes.
Okay.
So we just do the chain rule for that?
Yes.
What would dz dx be?
So dz dr would be what according to the chain rule?
dz over dx times dx over dr plus dz over dy times dy over dr.
Right. So what's the partial of z with respect to x? Well, we actually don't know. So you can just call this f little x. Partial of x with respect to r is cosine theta. Partial of y with respect to r is sine theta. An answer like that would be fine. Any other questions? Anything else from 11.5? We'll get to 11.6.
39?
39. What does that say?
Z equals f of x minus y.
F of x minus y?
Yeah. It says show that the partial of z with respect to y plus the partial of z with respect to x equals 0.
Okay. What's the partial of z with respect to y? Right. So beside the chain rule, differentiate the outside, multiply by the derivative of the inside with respect to y. That's just -1. So this is just this should be y. Equals what? Oh, well, negative. So this means you have fx this means you have dz dy plus dy dz, is that what they said? Equals, you have fx, well, let me write it in a better notation because it wouldn't be a partial. It'll actually be the derivative of the outside, right? You take the derivative of the outside function, multiply by the derivative of the inside function. So this would be this minus plus this equals 0. So this is sort of using the chain rule in the old-fashioned way that you used to think about it. Differentiate the outside, multiply by the derivative of the inside. With the y, you'll get a negative sign, and the x, you stay a positive sign, so when you add them together, you get 0. Anything else on 11.5? Okay.
What was 39 with you?
11.6. Wait, I think Clyde had a question first. What was it? It was 39.
Okay.
What did it say? Is it one of those word problems?
Yeah.
Anyone has a copy? Alright, so 39 says if f of x equals x times y, f of x, y equals x times y, find the gradient vector at 3, 2. Then use it to find the tangent line. To f of x, y equals 6 at the point sketch level curve, tangent line, and the gradient vector. Okay, so let's start with the gradient. Gradient of f is equal to what? Partial x, comma partial y, which in this case is, huh? Yx. So if I evaluate that guy at 3, 2, the result is just 2, 3. So that's our gradient vector. So now if we want to find the tangent line to this guy, what do we do? So let's look at the tangent line. What's the direction vector for the tangent line? Huh? What do we know about the relationship of the gradient vector to the tangent line? They should be orthogonal. What's the direction vector for the tangent line? Negative 3, 2 or 3, negative 2, something like that. So this means tangent line is going to be what? What's the equation of the tangent line? X, Y, Z equals. Do they want this in 3D or 2D? XY would be equal to the point
3, 2.
Right, it's at the point 3, 2 plus t
2
times.
Negative 3, 2.
That's your tangent line. And so now we have to sketch everything. So let's look at the sketch. I'll just do the sketch in the XY plane. What does it look like in the XY plane? What does it look like in the XY plane? We want the level curve f of xy equals 6. So remember that f of xy equals 6, which is equal to xy, which means I can say y is equal to 6 over x, right? So it looks like this. That's our level curve. We are at the point 3, 2. So that's our point. So what is the gradient vector is 2, 3, right? So this is just means you move 2 to the right, 1 up. 3 up.
Okay.
Right? Your tangent line is going to be orthogonal to that. Technically, this would be the vector. I think we'll take the negative of that one. Right, for our purposes, this can be thought of as equivalent to that. They're parallel. So that's the tangent line, 3 minus 2. xy equals 3 2 plus t times 3 minus 2. Other questions? Let's see what we You said which one? 41? Is 41 what you said? Show that the tangent plane to the ellipsoid flaw at the point flaw can be written as flaw. Okay, who attempted that one? Yeah? So you find the gradient vector. So the partial with respect to x is what?
2x over a squared, comma 2y over b squared, comma 2z over c squared.
Right, so the gradient, we want to find the tangent plane at the point x naught, y naught, z naught, so we just plug in x naught, y naught, z naught here. X naught, y naught, z naught. Right, and this is actually, it's equal to the normal vector of tangent plane. Forgot your exam.
Then use the form of the plane.
Now you just use the form for the plane. So you know that tangent plane. You have the form. Now you know how the normal is, how you get the normal. It's the partial of x with respect to x minus x naught plus partial of y with respect to y minus y naught plus partial of z with respect to minus times z minus z naught equals 0. fx is basically 2x naught over a squared times x minus x naught plus plus 2z naught over c squared. Now what? You can divide both sides by 2, get rid of all these 2's. And multiply out seems to be what you're going to want to do. So multiply this out, I get x times x naught over a squared minus x naught squared over a squared plus y times y naught over b squared minus y naught squared over b squared plus z times z naught over c squared minus z naught squared over c squared.
And you bring all the negative terms
So
to
bring
the
all the negative terms to the other side. Right? And what's that guy? It's equal to 1 because it's at a point on this ellipsoid, and the ellipsoid says this is how x, y, and z relate to each other. So that guy is just 1. Other questions? Huh?
On this side, it looks like it doesn't cover the whole board.
Are you missing?
Not a lot, but if somebody can get out, because they might miss it.
Zoom out a little bit. That's fine. Okay. 49.
Yeah.
Line to curve of intersection.
This parabola z equals x squared plus y squared. And the ellipsoid 4x squared plus y squared plus z squared equals 9. At the point -1, 1.
Okay.
I solve for z in the right hand, in the second equation. Instead of equal to each other.
Right, so I know z is equal to this, so I can just take this and plug it in here. And what happened?
We got x4 plus 2x squared y squared plus y to the fourth equals 9 minus 4x squared minus y squared. Sorry, that's moving around a little bit too.
9 minus what?
4x squared minus y squared.
Okay. That's as far as you got.
I mean, I tried a bunch of different things, but
Okay. Does anyone have any? Yeah. What do you think?
Because they gave us a point on the line of intersection. If we just find,
Where did they?
at negative 1, 1, 2.
Yeah.
So then, if we find the normals to the tangent plane, should be orthogonal to that line of the two equations. So like, put everything on one side and
Yeah.
equal to 0.
Yeah. So what are you trying to say?
So if you do that cross product, then we can get the direction vector of the line of intersection.
Yes, that's true. So you found the tangent planes to these
Well,
to each of the points.
I found the normals of the tangent planes, which are orthogonal to the line of intersection, and then cross product them.
Yeah. Do you see what he said?
I think I should.
Do you understand why it would work?
Well, I mean, yeah.
So one is a I don't know if it would be instructive for me to draw this.
You make them.
But basically, let's say one surface is doing this thing, and then another surface is doing its own thing, and they intersect here, right? I mean, if I can find a tangent plane to this guy, basically the tangent line to this curve of intersection is going to be orthogonal to the normal for this guy, because the tangent would have to be tangent to both surfaces. So the tangent has to be orthogonal to the normal for the first tangent plane. It would also have to be orthogonal to the normal for the second tangent. Because it's a tangent to both curves, so it's perpendicular to both their normals. So what he did was he found both their normals and just cross-brought them to get the direction of the tangent line. Right? And once you do that, you have the point, you can find the line. So now the question is, how did you get the normals? Just the gradient vectors, right? So you talk about this one. That's, what do we call these? S1 and S2. Surface 1, surface 2. So for S1, we need to find the gradient. What does the gradient look like? Right, so remember how we found the gradient. You have to bring everything to one side so it equals a constant. You decide to bring these over that side. I would have brought this over, but it's fine. So you looked at this as z minus x squared minus y squared equals 0. Then you take all the partials. So you get negative 2x, negative 2y, and 1. Which means at the point minus 1, 1, 2, we have 2, negative 2, 1. So this is actually the normal for the first one. Then for S2, I looked at the gradient of f. So this is going to be 8x, 2y, 2z. So at negative 1, 1, 2, we end up with negative 8, 2, 4. That's the normal for the second guy. So now for a tangent line. We already know the point is 1, 1, 2. The direction is just going to be n1 cross n2. n1 is 2 minus 2, 1, and 2 is minus 8, 4. So that's what? Minus 8 minus 2. Then the middle one is 8 plus 8. But then you take the negative of that. Then the last one is 4 minus 16. Alright, so that's... I can take anything parallel to this. So I can even scale this if I want to. It's equivalent for me choosing... I can divide everyone by minus 2. So x would be minus 1 plus 5t. Y would be 1 plus 8t. Z would be 2 plus 6. So that just comes from the idea of knowing that the tangent line is orthogonal to the gradient vector, right? And since this is a tangent line of intersection, that must happen to each surface. And so to find something that's orthogonal to those two directions, you take a cross product in the end, and that gives you your direction of the tangent.
Can we always simplify by cosine that? Like, could we have simplified negative 8 to 4?
You don't have to. I just do it like if you left this as minus 10, minus 16, minus 12, it'll still be right. You'll get all the same points. It's just that your t would be different values to achieve those points. Any other questions? The next section starts out with a lot of writing. I don't know how much you can get through by 10 class. Okay, so temperature T in a metal ball is inversely proportional to the distance from the center of the ball, which we take to be the origin. The temperature at the point 1, 2, 2 is 120 degrees. Find the rate of change of T at that point in the direction towards that point. Show that any point in the ball direction of greatest increase temperature that points towards the origin. Okay, let's do that one. So yeah, a problem like that. But a problem like that, at that level of difficulty, it's actually possible on a final, so we'll definitely do that. I was trying to look for another nice example that would show up on a final. But I guess when you're reviewing, you'll see. Let's see. So T is the temperature in a metal ball, right? We're taking the center of the ball to be the origin. Okay, so how can we describe the temperature T?
T is equal to 1 over radical x squared plus y squared plus c squared.
Alright, so technically proportional, you need a k here. You need a constant proportionality. So k is just a random constant. I don't really see information here, constant of proportionality. So far I don't really see anything here to suggest that it has to be 1, so I'll just leave it as k for now. And do you understand where he got this from? The distance from the origin, right? So a random point on this sphere, x, y, z. I look at the distance from that and the point 0, 0, 0. Right? So I just do the distance formula basically. The distance between that point and the origin is the radical of x squared plus y equals z squared. Inversely proportional means it's proportional to the inverse of that. So that's how we came up with this formula. So they never gave you the formula here, you have to figure it out. Like this you have to just figure out. Right? Just by doing a distance formula. So now we know the formula. I want to know, so I know T. I know that T at 1, 2, 2 is 120 degrees. What does that mean?
You will substitute 120 in the point in the bonus.
Right, so this means 120 is equal to k over the radical of, I plug in these numbers for x, y, and z. So it's 1 plus 4 plus 4, right? So that's 9, so that's 3. K is equal to what? this means this is my function t. So it won't actually be a 1. The constant proportionality in this case is 360. So that piece of information helped us find that k. Now what do we want to do? I want to find the rate of change of the temperature at this point. No. Rate of change of T at 1, 2, 2 in the direction 2, 1, 3. How do you find that?
Just find the vector. The vector do with the 1 comma negative 1 comma 1.
Right. Final minus initial. You do 1 comma negative 1 comma 1.
And you just find the unit vector.
And we need to find the unit vector. So it's just 1 over radical 3 minus 1 over radical 3. 1 over radical 3.
Then you have to find the gradient.
Then we need to find the gradient of the temperature, which is, we're going to have to find the partials of that guy. So this is partial of t with respect to x, partial of t with respect to y, partial of t with respect to z. They're all going to look very similar. What's the with respect to x?
Negative 360x parentheses. Oh yeah, okay. X squared plus y squared plus z squared around parentheses to the 3 halves.
Right, the others are going to be very similar. It's going to be 360y over that. Comma, the last one's going to be 360z over that. So at the point of consideration is 1, 2, 2. The gradient at 1, 2, 2 is, what's going to be the vector? Negative 360 over
52.
how do you get 52?
I plugged that. I mean, I don't know, I did the math wrong. I plugged in, just plugged in the point.
Right, you're plugging in x is 1, y is 2, z is 2, right?
Yeah.
It means you get
Oh,
9.
oh,
So you get 9 to the 3 halves, which is 3 cubed,
27.
27. Does that divide nicely?
Yeah,
Anyway, so this is minus 360 times 2 over 27. This is minus 360 times 2 over 27. 27 goes into 360?
it's a fraction. 40 is negative.
Negative 40 over 3. So this one would be negative 80 over 3. And so now the rate of change rate RC five. Now you just talk power terms for the rate of change. So it's minus 40 over 3, minus 80 over 3, minus 80 over 3, dot product. 1 over radical 3, minus 1 over radical 3, 1 over radical 3, which is just 1 over radical 3 times 1 over 3 radical 3 times 40 plus 80 minus 40 plus 80 minus 80. So we add 80 and subtract 80 and we just get minus 40 over 3 radical 3. So it means as we're at this point and we're moving towards that point, our temperature is actually dropping. We're actually getting colder. So that's the rate of change. What else do we want? Any point of that? Okay, so how do we, what's the direction of greatest increase? Let's continue with here. Direction of greatest increase. It says show that at any point in the ball the direction of greatest increase in temperature is given by the vector that points towards the origin.
You have point ABC.
Yeah, so remember direction of greatest increase is given by delta T. Which we already found. Minus 360x over at the point let's say ABC.
Can you just factor out negative 360 over x plus square root of 3 times with scaling? And you just want x, y, z?
I could,
Is that
yes.
good enough?
Come again?
Is that good enough? Because it says at any point?
Yeah, so I'm saying ABC is any point.
Okay.
Direction of greatest increase is going to be, yeah, I can take out this minus 360. This is x over basically, what was my t was, my brother writing this stuff. How do we know this points towards the origin?
When you plug, as soon as you plug in a, B, and C, it's just scalars of x, y, and z.
Right, so this guy, it's just scalars of x, y, and z. You can think of it that way. They're all proportional. One goes in the x direction, one goes towards the y direction, one goes towards the z direction. They're all negative, so you're always moving in the negative x, negative y, negative z. You're always moving inward and downward. This is towards the origin. Because you can think of the vector x, y, z as going out the origin when they're all positive. Any other questions? So yeah, that's actually a nice final problem. So
Can we do what 21?
where they don't directly mention any of the buzzwords that you might use. So they never like mention the word gradient or anything like that. They say rate of change and things like that. Describe a physical situation. You're the one who has to recognize it. Oh, I'm supposed to take the gradient and dot product it. It's a directional derivative. Which one are we doing?
21.
So in 21, we're given a function f of xy, x squared plus y squared minus 2x minus 4y. Show, no, find all points where direction of max increase is ij. How do you find that?
I found the gradient.
Right, the gradient is the direction of max increase. So you find the gradient, you get what?
2x minus 2 minus 2y minus 4.
2x minus 2, 2y minus 4. So what do we need here?
The direction.
I want to find all points where the direction of max increase, i.e. this guy, is that guy.
Oh no, sorry, so you say, I get it, okay. So you set that equal to the direction.
So basically you want 2x minus 2, 2y minus 4 to be equal to 1, 1. Which means my x must be what?
3 halves.
Huh? Y must be what?
5 halves.
So a point is 3 halves, 5 halves. What will be the z value at that point? Well, you plug it in here. Whatever. This is f of 3 halves, 5 halves.
Did they ask for all points?
Huh?
Did they ask for all points where that was true? That the max rate of change was in the direction of like
Yeah, but since it's linear, it's only one. There is only 1 point.
They ask for all points. So what you can do is you can scale this one. Yeah.
I did it a bit differently because as soon as you get this to n, I kept it in terms of I and j. So you have 2x minus 2y, 2y minus 4j. Has to equal I and j, which means 2x minus 2 and 2y minus 4 has to equal each other.
You'd get the same thing in the end.
end it with a line.
If you do what?
If you act equal to each other, if you set equal to
Because for all
2x minus
It's all
2.
points of I on that line.
That's what I did at first, but that was wrong.
If you
I'm not. Let's.
You basically set up a system of equations, 2x minus 2 equals 1 and 2y minus 2 equals 1.
You wrote it as you wrote gradient f in terms of I and j, as in 2x minus 2i plus 2y minus 4j.
And we were told that that equals plus j. So that means they must be equal to each other. 2x plus 2y plus 4 or no?
So this means
2x minus 2 equals 1
2x minus 2.
Equal to 2y minus 4.
since our they are multiple points.
Because if it was
2y minus 4.
multiple to
Oh, I see what you're saying. Okay.
That's why we get more points than this one.
So you can divide by 2, get x minus 1 equals y minus 2, in which case you get y equals. So the points will look like what?
all points on the line.
X plus 1, comma f of x plus 1. Right? You have to make sure that they're on the line. In addition to that, you could just scale this, so you know that all points are parallel to this also. But you'd have to make sure that your z coordinate matches with the points you pick, so you need to throw this in guiding. So we can stop there, hand in your homework. We have 2 homeworks on the MATLAB homework today.
I also have 6. So